And I would like to thank the organizers for inviting me and the local organizers for putting this together. It's really nice to be back in Bonn. Right, so this is to be about type 3 factors, joint work with Yusuke Isono. And let me start with some brief introduction about the problem and Haagerup Størmer's conjecture. So first of all, let's start with the definition of pointwise inner automorphism. So here we start with a fundamental algebra, and I denote by M substar the predual. And the action of the automorphism group of M on the predual is of course by pre-composition. And then we said that an automorphism of M is pointwise inner if for any given positive normal form on M, the action of theta on phi is by an inner automorphism. That will a priori, of course, depend on phi, of course. Phi. So, of course, any automorphism is pointwise inner. And it follows by Radon-Nikodym co-cycle theorem from his thesis that in fact any modular automorphism is also pointwise inner. So then, of course, this the set of pointwise inner automorphism it's a subgroup. So the composition of inner and modular, of course, are pointwise inner. And then the question is whether there are other automorphisms. And this is this question that, oh yeah, just a disclaimer. So in my talk, all fundamental algebras have separable predual, okay, to avoid any counterexample or things like that. So back in the late 80s, early 90s, Haagerup and Størmer, they wrote a series of papers in which they discussed this question and solved the problem in many situations. And so let me state just in one theorem sort of the main results they obtained. So for trivial or more generally for semi-finite fundamental algebras, then the only pointwise inner automorphisms are in fact inner. Okay? They also completely settled the question for type 3 lambda factors where lambda is different from 1. And then they showed that pointwise inner automorphisms, they are the composition of, say, inner automorphism and an extended modular automorphism. Okay? So here what I wrote is, it doesn't matter, but C is a 1 cocycle from R to the unitary group of the continuous core of M. But I will not go into that. And for the type 3-1 case, they managed to show that for the Araki Woods factor, so the only type 3-1 factor that is AFD, then they showed that indeed any pointwise inner automorphism is the composition of an inner and a modular automorphism. And then in one of their papers, they asked this question, and actually they state it as a conjecture. And the conjecture is that whenever we have a type 3-1 factor with a separable predual, then in fact any pointwise automorphism should be the composition of inner and modular. And so quite interestingly, up until now, the Araki Woods factor in fact was the only type 3-1 factor for which the conjecture was known and was proven. So the idea here of this work and today's talk is that sort of building on Haagerup and Størmer's work and using some 21st century tools, we can provide a large class of type 3-1 factors for which the conjecture is satisfied. Okay, so let me give you the sort of the main results we obtained. And in order to present the result and to state it in a nice and friendly way, I will just recall the definition of an almost periodic factor. So it's very simple to define. So whenever you have a fundamental algebra and you fix a faithful normal state on the fundamental algebra, so remember that the fundamental algebra has separable predual. Okay? So whenever we have a positive real, we can consider the space of what we call sometimes the lambda eigen operators. Okay, so we look at the set of elements in M, such that we have this sort of relation, so x does not commute with phi, but x phi is lambda times phi x. Okay? So equivalently, this is saying that x is really an eigenvalue for the modular automorphism group, so sigma t phi of x is equal to lambda to the it x. Okay? So we have the set of eigen operators for lambda, and then we said that the state phi is almost periodic. If in fact the linear span of all these subsets is strongly dense in M. And then sometimes I will refer to the point spectrum of phi, or the modular operator, as the set lambda for which the corresponding eigenoperator subspace is non-zero. Okay? And then we just say that a fundamental algebra or a factor M is almost periodic if it admits, it possesses an almost periodic faithful normal state. Okay. So some example. Well, of course, any threshold fundamental algebra is almost periodic because it has a trace. Any type 3 lambda factor for lambda different from 1 is also almost periodic. So for lambda between 0 and 1, we can just take the periodic state. And then it's a result due to Kohn that on any type 3 zero factor, you have plenty of almost periodic states. And also, of course, the Araki Woods factor, R infinity, is almost periodic because you can write it as a tensor product of two AFD factors, one which is type 3 lambda and the other one which is 3 mu, where lambda and mu are well, log lambda over log mu is irrational, something like this. Okay. Okay, so we have two results, and I will try to explain you the main ideas of the proof and actually give you a sketch of the proof. So the first result deals with tensor products. Okay, so what we show in the first result is that actually many McDu factors, they do satisfy the conjecture. So the result is like this. Let's take any type 3 factor that is almost periodic, so possesses a nice state. And let's assume that it's McDu in a rather strong sense. So let's assume that it absorbs tensorially R infinity. Right? In particular, it will absorb R, but let's assume that it absorbs R infinity. Then M satisfies the conjecture. Okay? So this is the first result. So this deals with the tensor product construction. And the other one is the free product construction. So in fact, I will not state the most general version because it's a bit technical, but let me just state one sort of corollary. So we can show that, in fact, any almost periodic free Araki Woods factor, so the one coming from this sort of twisted version of Voigt-Kolyszko's free Gaussian functor introduced by Dimash-Latenko, then all of these factors, they satisfy the conjecture. Okay. So then we have two different families, actually two disjoint families, okay, that satisfy the conjecture. The first one, they are McDu, so they have lots of central sequences. And the second one, these factors are full, so they have no central sequences. Okay.
Excuse me, if you have to check pointwise independence of an automorphism, do you have to check all states or a single state?
I guess you have to check for all states.
Okay.
Yes. Okay, so we have these two results, and you might say, well, okay, so you can handle tensor products, you can handle free products, maybe you can handle everything. I strongly believe it should be true in general, but our method, there is sort of an obstruction, and I will explain it where it is. And it's unclear whether or not we can go beyond, either tensor or free product. Okay, so I will come back to this. But just let me give you a sort of a brief outline of the strategy. Actually, our idea is really simple, really simple. What you do is you start with type 3 one factor that arises in theorem A or B, and you start with any pointwise inner automorphism. So because of the setting of theorem A or B, we have a nice embedding of R infinity, whether it's in a tensor product position or it's in a free product position. And this theta, we can show that up to unitary conjugacy, it will leave invariant this nice copy of R infinity. So that's one thing. So now we have sort of an automorphism that preserves the pair, the embedding, the pair of vectors. And then again, because of the algebraic nature of the embedding, we can show that the restriction of theta to R infinity, we don't know whether it's pointwise inner, but it's pointwise inner in a loose sense. It's locally pointwise inner. So it's weaker, but still it retains, you know, some of the properties of pointwise innerness. And then we use sort of a big gun, so then we use the Kawaidashi-Suzwaran-Takezaki's classification of automorphisms of R to actually deduce that the restriction of R to R infinity is modular. And then because of almost periodicity, then we can in fact deduce that it's modular on the whole type 3 one factor. Okay? So then the simple idea is to restrict to a nice embedding of R infinity, and this embedding, we can still retain some information about the pointwise innerness, and then use, you know, all that we know on R infinity, classification of automorphisms and so on and so forth. Okay? I will come back to this brief outline, and I will sort of sketch the proof of theorem A at the end of my talk. Okay, so what is this notion of locally pointwise automorphism? Before doing this, I need to recall an important tool which I like to call the intertwining of normal states. So let's assume that we have a fundamental algebra in a positive normal form. So for us, it will be important to allow the states of the normal form not to be faithful. Okay. So then they have a support projection in M. And then with this normal form phi, I will look at all the faithful element capital Phi, again in the positive part of the trivial, that extend little phi in a nice way. I want this support projection to be in the centralizer of capital Phi. Okay? So that's why I denote it by script E phi. And then we have this result that we obtained 6 years ago with Dima and Stefan. Actually, I talked about this in Bonn 2016. So. Okay, so let's take two normal forms. Let's assume that they are non-zero. And let's take two nice extensions. Doesn't matter which one we choose, but let's take extensions. And so we have the following two equivalent statements. So the first statement, as you can see, this is really a purely algebraic statement. Roughly it says that there exists a non-zero partial isometry that up to a scalar conjugate phi onto psi, right? So we need to allow this non-zero partial isometry. It's not necessarily unitary, and we might have, you know, a scalar, because after all, I do not assume that phi and psi are states, right? So we need to allow this, this amplification. And the second statement, it's more an analytic statement, and it says that actually we cannot find a net, or here rather a sequence of reals, so that if I denote by Wj the conderivative between capital psi and phi, then I have this sort of mixing condition, okay? So that I wrote. So this is really an analytic statement. And if one of the two conditions is satisfied, we say that psi and phi are intertwined. Okay? So this is really a symmetric relation. And of course, for my deformation rigidity friends, they of course immediately recognize it's kind of an analog of Popa's intertwining theorem for subalgebras, right? It's a very nice and important tool, and it's really like typical fundamental algebra, right? It's like bicommutant. You have sort of an algebraic characterization and then an analytic characterization, and that's why it is so useful, right? This is fundamental algebra. Okay. So now I can define the notion of local pointwise inner automorphism. So the reason why we introduced this is because typically it's extremely difficult to check that an automorphism, say, okay, we start from a fundamental algebra and we have an automorphism that preserves, a subalgebra, and we would like to prove that on this subalgebra it's still pointwise inner. Then we need to construct or prove the existence of a unitary that, does the conjugation. And typically when we intertwine subalgebras into n factors, typically it's hard to construct a unitary. But, we might get, something weaker like a partial isometry. And then using some sort of maximality argument, using factoriality or ergodicity, then we can, from this local thing to get, a global unitary intertwining, what we have. And basically this is the idea here. So here I allow this not necessarily to have a state, but a weight. Strictly semi-finite just means that the weight is semi-finite on its centralizer. So it's important to allow this general statement here. Okay, so we said that theta and automorphism is locally pointwise for phi. If, well, first of all, it preserves phi. And then it will do, typically what pointwise inner automorphism do, but for a particular class of states. Okay. So here, what the condition is that slightly technical. It says that for any non-zero projection in the centralizer, which has finite weight. Of course, if phi is a state, you can take any projection. And every positive invertible element in this corner of the centralizer, then you see you have phi h, which is just the cut down of phi by h. And I want that phi h and theta phi h maybe not to be unitarily conjugate, but just intertwine. Okay? So this local thing is just because we cut down by any projection and we look at these very specific states. A few remarks are in order. Well, first of all, if we start from a pointwise inner automorphism, and we fix this phi, then up to unitary conjugacy, theta will be indeed locally pointwise inner for phi, as it should be. And also this property is quite nice because, for instance, if you take phi to be, say, a faithful state, such that the centralizer is a 2n factor, then this notion passes to amplification. So if theta is locally pointwise inner, then theta tensor the identity will also be locally pointwise inner. So it has this nice stability property. Okay? And what's interesting when we deal with almost periodic states or almost periodic weights is that we can give a sort of a complete nice characterization of such automorphism. And here the setup is as follows. So we take a fundamental algebra, or rather a factor that has an almost periodic state, and I will moreover assume that the state is extremal. So extremal means that the centralizer of my state is large. Okay? So it's an irreducible subfactor. So then the point spectrum of the modular operator is countable because it's about point triple, and here because of extremality, this ergodicity property, then it's a subgroup. And I denote by G, the dual, the Pontryagin dual, which is a compact group. And then what's nice is that you have the modular automorphism group of phi, and by almost periodicity, then this modular automorphism group will extend uniquely to G. So now you have a nice action of a compact group on N. Okay. And here is the result. So let's assume that we have an automorphism that preserves phi. And so we have the following equivalent condition. The first one is it's locally pointwise inner. So this slightly technical notion. The second condition is just innerness on the centralizer. Okay, so because the automorphism preserves the state, it will leave globally invariant the centralizer. And on the centralizer, it's inner. And then the third condition, maybe the more, the nicest one, is that actually we can explicitly write in theta and say what it is. Actually, there exists a unitary in the centralizer, and there exists an element G in G, such that theta is at W composed with this sigma G. Okay? And then the game, you see that will be to deduce that if we have something that is locally pointwise inner, we have this way of writing it. Then, you know, removing W, we can write it as sigma G phi. And then the whole thing will be to try to find ways to say, well, this G, which is in the compact, you know, closure of R, is actually in R. Right, so we will need, you know, some other argument to show that really G is in R, and then to deduce that theta is indeed modular. Okay? But this is certainly one of the tools that we will use. One key ingredient behind this theorem is a theorem I like a lot by Cyril Popa from '82. So Sorin proved lots of results constructing examples of massas with various properties. Singularity, mixing, whatever. And then I guess this result was the first one along these lines. And it showed the following nice result. So let's take M to be semi-finite, fundamental algebra. And let's take script G, a subgroup of automorphisms of M, such that the image of G in the outer automorphism group is countable. Then Sorin showed that there exists a G singular massa in M that is generated by finite projections. And basically what it means, G singularity, it means that if theta lives invariant L, it means that theta must be the unitary conjugacy by a unitary coming from L. Okay? Right. And in our situation, we will use this result and we will apply this result to the semi-finite fundamental algebra coming from the discrete core and the trace scaling action. These last two lines just for the type 3, you know, aficionados. But let's just give you, explain you how we can use Sorin to prove sort of easy version or a key element in the proof. So let's prove this this result, and it's actually completely analogous to the result of Hofer, Haagerup, and Haagerup Størmer, showing that semi-finite fundamental algebras have their pointwise automorphisms are always inner. So this is really the analogous statement. Okay, so let's take a 2 infinity factor, and let's take an automorphism that is locally pointwise inner for the trace. Okay. And let's just show that it is inner. Right? So we need to construct a unitary. Okay, so how does the proof go? So look at the group generated by theta, and then you apply Sorin's theorem, and then you obtain a nice G singular massa in M, such that the trace on A is semi-finite. Okay, so A will be with a trace preserving conditional expectation. Of course, because we are in a separable setting, so of course A is generated by a nice self-adjoint operator. That's denoted by H. And now let's take any non-zero finite trace projection in A. This is why now we use the local pointwise innerness assumption. And basically what we have is that the state tau of HP and theta of tau of HP, they are intertwined. Okay? So then we have the existence of kappa and non-zero partial isometry, such that we have this algebraic relation. So this is where we use the assumption of local pointwise innerness. And then because we have a massa, we can assume, say, we always need to be careful with the support of the non-zero, the partial isometry, but here we can assume that V star B is P, and V star it's coming from a projection in A, right, by theta. And so doing this by shrinking the support, then we have like a partial unitary conjugacy between theta HR and HP. But because here we have a 2 infinity factor, this partial isometry, we can extend it to a unitary. And so what we have is that at W star composed with theta preserves A, or a corner of A. And then we can use the G singularity to deduce that at W star composed with theta is inner. And so theta is itself inner. Okay? So this is how we use Størmer's result. And actually this is how also Haagerup and Størmer they use Størmer's result. And quite interestingly, when you read their paper, so they state as a proposition that semi-finite fundamental algebra only have inner pointwise inner automorphisms. And there is a paragraph before the proposition that says that actually this idea of using Størmer's result was suggested to them by Ron Jones. Okay? So I think it's kind of nice to mention that. All right, so as I said, so this is one tool here, this local pointwise innerness. And we get that if we have something that's pointwise inner up to some noise, up to unitary conjugacy, we get something that looks like modular automorphism. But it's still in this compact extension. So now we need another tool to say that, well, this G actually is in R, equal to T. So we need another tool, and it will not be always the case. And so that's why actually now we need to restrict to either tensor product construction or field product construction. Right? And let me introduce this notion of intertwining stable inclusion. It's a bit ad hoc, but yeah, bear with me. Okay, so now we are in the situation where we have an inclusion of fundamental n in M. So the usual setup is that we have a nice, faithful normal conditional expectation from M onto N. And we have a nice, state that leaves, invariant the conditional expectation. Okay? Equivalently, the modular automorphism group of phi leaves invariant N, okay, by Takesaki's result. Okay, so we introduce the following sort of ad hoc terminology, and in words, let me explain what it is. So we have this inclusion N in M, we have this expectation, and let's assume that we are in the situation where the automorphism I'm looking at, it's not just an automorphism of M, but actually it's an automorphism of the pair, right? So this automorphism leaves invariant N and behaves nicely with the conditional expectation. And also let's say that it preserves the state, right? So we're in a nice setup. So we have this fixed state, okay? And now what I want is that I want, in this definition, that's why it's non-trivial, I want that for any normal form on N, psi, when I compose it with E, of course I get a state or a form in M. And what I want is that if psi composed with E and theta of this are intertwined in M, I want actually that they are necessarily intertwined in N, right? So, of course, if I get an intertwining in N, because N is in M, I will get an intertwining in N. But you see that the other way around, it's not automatic. So let's make it a definition, right? So, and that's why we call this inclusion intertwining stable, for lack of a better word, but I guess that's okay. And of course, the key observation, and it's really why we introduce this notion, is that if we have, the nice setup, and in M, conditional expectation, a state, so on and so forth, let's take now any state or weight on n. If the inclusion is intertwining stable, and if theta is locally pointwise inner upstairs, it will be locally pointwise inner downstairs, right? This is what we want. And this fits very well with my initial, rough strategy. My strategy at the beginning was that, okay, I have an inclusion, I start with a given automorphism that is pointwise inner, and I would like that by restriction on the subalgebra, I wanted to preserve some sort of pointwise innerness. This is the device that we need. Right? So if the inclusion is intertwining stable, then I get this nice step that we have stability of locally pointwise inner. Of course, the lemma is 2 lines using the definition, but just let me state it as a lemma. Okay, so if we have intertwining stable inclusions, then we can sort of start the engine, starting the proof, and then we can do something. Now we need examples of intertwining stable inclusions, right? The first easy example is the tensor product construction, right? So if n is in a tensor product situation in M, and if I take, for instance, phi to be tensor product of state, and if I take the expectation to be, the identity tensor state, then everything, works very nicely. I get that the inclusion is intertwining stable. This is, fairly easy to prove. The second one requires a little bit more work, using a little bit of free etymology techniques and so on and so forth. And the second example is the free product construction. So now n sits in a free product situation in M. The state phi, this is, say, for instance, a free product state. And the expectation, this is the only phi preserving conditional expectation, it's identity star, say, phi p. Assume moreover that, it's technical, but assume moreover that the centralizer of n is a factor, then the inclusion is intertwining stable. Okay? And of course, to prove this, we need the analytic characterization of, intertwining. Right? Because the definition to prove intertwining stability, we need to prove that if we have intertwining upstairs, then we have intertwining downstairs, and then actually we prove the contrapositive. We prove that if it's not intertwined below, it will not be intertwined upstairs. And so, having this net that witnesses the non-intertwining, then we can lift it to M using these, algebraic, construction, either tensor product or free product. So that's why the result that we have with Dima and Stefan is absolutely crucial. Okay? But actually, they are counterexamples. So they are natural examples of inclusions that are not intertwining stable. And let me give you one. And I think this sort of counterexample sort of gives sort of an obstruction for method to really to go beyond either tensor product or free product construction. So the example is as follows. Take R infinity, so the AFD type 1 factor. Let's take on it extremal almost periodic state and consider the Bernoulli action. Bernoulli shift by Z, just by Z. So look at the Z action. Shifting, permuting the indices. Let's call N the infinite tensor product, which is of course still, it's isomorphic to R infinity. And let's set M to be the cross product. Okay? So we have N inside M that sits in a very natural way. I mean, it's a cross product. So of course you have the canonical conditional expectation, just looking at the Fourier coefficients. And then of course you have a unique state, extending the the infinite tensor product state and preserving the conditional expectation. Right? Then the inclusion is not intertwining stable. Okay? And the proof is, well, it's not difficult at all. It's just actually it uses our characterization of locally pointwise inner automorphisms. And to see that it's not intertwining stable, we need to, that an automorphism that is, very simple. So why it's not intertwining stable? Well, we use our characterization, but the example is pretty clear. So you see that you have the shift, right? That permutes, the indices. The shift on the cross product, it's, it's a unitary, right? That's why we introduce, cross product construction, because then the shift is just an inner automorphism on the cross product. So then, being an inner automorphism on the cross product, it's of course locally pointwise inner because it's inner. So if the inclusion were intertwining stable, we would get that the shift on n should be locally pointwise inner. But it's not, because it shifts, the permutes, the copies. And if it were pointwise inner, it should be, extended, modular automorphism. But it's not the case, right? So that's why, this really simple approach that we have cannot work in general. It works only in very specific situations. Okay, so let me just give you a few, explain how all of this work, putting all this together. Let's first look at the theorem A, so the tensor product situation. Right, so the setup here is as follows. So we take type 3 one factor, and we get an almost periodic state. And let's assume that M is isomorphic to M tensor R infinity, so it absorbs R infinity. Then let's prove that it satisfies the conjecture. So what I will do here is I will write M as tensor product N tensor P, and N for me will be R infinity, right? So I can certainly write it like this. And what I can do, because it's a tensor product situation and R infinity has many almost periodic states, actually what I can do is choose a state phi on M that I can write as a tensor product state, and I can choose it in such a way that it is extremal, and actually phi n also will be extremal. And the state and its restriction to n, they have the same point spectrum. Okay. So I can do that. And here this point spectrum will be a dense subgroup of R. Okay, so now let's take pointwise inner automorphism, and I want to show that it's inner. Okay. So then, using the characterization that we have, because we are in an almost periodic situation, then actually up to unitary conjugacy, I can assume that theta is this modular extension by this compact group, which is the dual of lambda. Right? So theta is sigma g phi, where g is an element of the dual of lambda. And because it's this extension of modular automorphism, then theta will be invariant n. And everything is nice, preserve the state, it's And this is why we follow Haagerup Størmer argument. So actually, of course, n, which is R infinity, it will be isomorphic to R infinity tensor R. Right? And so using the Kawahigashi Tsuruga-Takesaki classification, we can write theta as the composition of a bunch of things. So we have a unitary U in the tensor product. We have an automorphism of the tensor product. We have beta an automorphism of R. And actually we can write theta as the composition of add U, conjugacy by pi, and sigma t phi, sigma t omega for dominant weight or whatever, tensor beta. So we see that the miracle here is using the classification of automorphisms of R, it appears here a T. Right? So here we have a certain modular automorphism, sigma T omega. And of course, we have all this noise, around with pi and adieu.
This is what data looks like on M or just on N?
No, now this is just on N. Yes, just on N. Sorry, I should have said that, yes, just on N. I should have written the restriction to N. Thank you. And the whole trick now is, forget about adieu. So theta, it's sigma T omega tensor beta conjugation by pi. And now theta, because I have this flexibility of changing the state on N, I can take, for instance, the state omega tensor tau composed with pi. Then now theta will be locally pointwise enough for this new state, this mysterious state that I don't know. Right? And here, what did I use? Well, I used the fact that the inclusion of N in M is intertwining stable. Okay, so I have this flexibility of choosing the state that I don't know anything about it, right? It's just arbitrary state on N. And then actually it follows, and it's very easy to prove that actually it forces beta to be inner. So beta just creates some noise that we can get rid of, and actually this further implies that G is equal to T. Right? So this is how we can prove that G actually is in R. And from this it follows that theta is indeed modular. So yeah, we use difficult result. We use the classification of automorphisms to do that. As Haagerup and Størmer did.
And this T that you get G equal to, that's the T in sigma T.
That is the same, yes, that is the same. And actually, in the whole proof, we use twice that the state is almost periodic. This remark is for you. Okay. So what about the free product case? It's actually basically the same proof. Okay, so this is about free Araki Woods factor, now not just Araki Woods factor, free Araki Woods factor. And so there is this nice classification theorem by Dima from the 90s. And to any countable dense subgroup corresponds a unique up to state preserving isomorphism, corresponds a unique free Araki Woods factor with a almost periodic state so that the con SD invariant is lambda. And now we use a beautiful result by Mike Arglas and Brent Nelson about classification results, and they showed that basically almost all free products of finite dimensional algebras or free product with AFD factors and so on and so forth, they are basically isomorphic to free Araki Woods factor. And so we use that result to write the free Araki Woods factor as a free product of R infinity, our nice, non-free Araki Woods factor, star say B of M2, star, just type 1 factor. And we can, we have a nice state preserving isomorphism, we can choose the state as we want. And then the rest of the proof is basically the same, okay? And you know what, I will stop here. Thank you very much.